right, we have been working in our workspace. In period 1, we did not get to this example yesterday, so if you need to, you can go ahead and pause this video at any time in order to get not only the steps for finding the second derivative, but also this example. You can pause it if you need it. I'm just going to scroll down. You can pause it if you need it. Had to plug in that dy dx in order to simplify, and then we found a final answer that we could not simplify further. Now, this is the example the kiddos were working on in their workspace. Guys, go ahead and check out the work that I have on the sideboard. Do you see how first I took the derivative of both sides? Oh, I'll remind you. I'll remind you now. Sweatshirt ideas for bonus participation, which is pretty cool because it's its own category. And it didn't even get added into the last grading period because I forgot. So it can bump your grade. That's exciting, especially if you get a bonus in there. Bonus participation point if you submit some sort of sweatshirt design. It does not need to be totally snazzily made online with one of those sweatshirt design sites. It can literally just be hey, I like this meme. Well, be careful on those. I like this joke. I like this idea. I like this emblem or this logo, and I think it should be on the sweatshirt. Just submit it. Print it out, submit it, or if you're an artist, you can design and then submit it. Yeah.
We asked this, but can we do your face of it, like on our sweatshirt?
People have asked that before, and I typically say no because I don't want my face on a sweatshirt.
It's like just you like this.
It could be a stick figure me.
Well, that's terribly.
My name can be on it, but besides that, no. Here's another dilemma. Think about every single color that needs to go into a design costs money. So think, fucking white version of me. So back to a stick figure of me. I can do that. Okay, so coming back, if you have any ideas, and P.S. my quick disclaimer: if you just Google calculus jokes, there will be inappropriate ones, and just be discerning. Life around us is inappropriate too. So just do the best you can and try to find something fun. I can't tell you the BC ones because we've already had some good ones, but anyway, I'm kind of excited.
Just give us their reference. You know what they throw out as a design, we'll accept.
Okay, well that's horrible. Coming back. Okay, so back here, that's due tomorrow by the end of the day. I just need something that is paper, or you can email it to me and I'll print it out, and in class tomorrow have you go run and get it from the printer, and then you can be like, look, here it is. Something that has your name attached that says, this is what I think would be fun. Okay, put your name on it too. I took the derivative of both sides, true?
True.
I needed product rule, true?
Yep.
And when I took the derivative of y, I needed a dy dx, right?
Yep.
How many of you guys got to this derivative of some shape and form? 4 minus 2xy all over x squared. Okay, those who didn't, do you have a question? 4 minus 2xy all over x squared. Does this make sense? Okay, so then I added the 4, because he doesn't have a dy dx. I subtracted the 2xy, because he doesn't have a dy dx. Then there's only a multiplication left. I divided the x squared. Yeah, I added the 4, subtracted the 2xy. This is left. I divided the x squared. Yeah, does that make sense? David?
I have a question.
Yeah.
I actually got caught up, and we know, like, you know, what you do it, but, like, how come you couldn't put the 2x, like, initially, before, like, deriving it? The x squared, you could make it 2x.
Oh, you do here with second d first, but when you go to do first d second, remember, you keep it the
Because
same.
of the product rule, you have to do it.
Yeah. So product rule second d first, you have to take the derivative here. But then when you do your second part of the product rule plus first d second, you only derive the second. You
So
keep it.
if the x squared and the y weren't connected, then you could derive it.
Then you could say 2x and you go. But since when you read it, it's x squared times y.
What was the first derivative?
4 minus 2xy all over x squared. Okay, this is because what are the directions? Find the second derivative. So when I went ahead, and for anyone in the video, I apologize, I have been working on the whiteboard because it was faster during HTTP. When I take ddx of both sides, and when I did get my little product rule, I was only finding the first derivative. This is just the first derivative, which is good. What did direction say?
Second.
Sean, where did that, or David, both of you found it, where did the second derivative start in homework? The 60?
49, I think.
Oh, the 40s.
49. It was 49.
Okay. So up to number 49, you were probably mostly just doing first derivatives, maybe a little bit of like review, but you were doing first derivatives. But then as soon as you hit number 49, as soon as you hit this direction, find the second derivative. Look on the board. I have to go again. So since I have to go again, I just changed colors just because, I don't know, I like writing UDX in a different color. So we're not going back to the original. It's not symbolic of going back to the beginning. We're going again. We're going one step further. And I was talking through with David with the notation. ddx is the verb. We need to derive the first derivative. That's the first derivative, the noun. This is the verb. Let's take a derivative of that. And if you look at this notation, hopefully you see and you remember, oh, d squared y all over dx squared. That's the notation. And it comes nicely out of how you write it.
So d over dx means that you're
Derive.
deriving it, but then
Yeah.
the dydx is a variable.
Derivative is a noun. So this is the first derivative. This says we need to take a derivative. So this is an object. This is an object. This is an action. Is that a better way of saying it?
Yeah.
Sorry, I thought. This is an object. No, that's not. That's not. Oh, this is.
No, it's fine.
I was like, oh.
No.
This is an object, a derivative, and this is an action. Let's derive. Does that make sense? Yes. I really like the idea. Calculus is driving me crazy. I've always wanted to put on a sweatshirt. No one's ever accepted it.
Okay,
like
that
it.
is nice.
Calculus is driving me crazy.
Yeah,
So it's supposed to be a
deriving.
llama.
Is the statement simple?
Just like a random llama. Well, I'm designing it, guys.
I like this one.
Okay, coming back. Oh, Optimus Prime. That one's funny too. I like that one.
Can we do that?
Optimus Prime because it's the Optimus over here. Anyway, coming back.
Then like that. I'm gonna do that. Pinterest is
How do I take the derivative over here?
Oh, you have to quotient rule.
Quotient rule. So I wrote it over there for you guys to check, but I'm going to go ahead and talk it through up here. Guys, let me finish this problem. It's our workspace. Okay, so I have a bottom and I have a top. True? Cool. All right. So derivative rule, give me the chant. You can look on the sideboard if you want. I'm writing it up here if you're like, I don't get what's on the sideboard.
Bottom D top.
Okay, pause. Bottom D top. Why is the top tricky?
Because that's a product rule.
Well, pause. What's the derivative of 4?
0.
0. Okay. Minus. Okay, you have a negative. Okay. It's a product rule because, ready? Read it. Negative 2x times 1. So we need a product rule. Now, I went ahead and put the negative with the 2x because it's a little easier than keeping the poor little guy outside. I put the little negative with the 2x just so he's in there when I do my product rule. Bless you. So second would be y, right? Second, d first, derivative of 2x is 2.
Wait, negative.
Ah, gracias. See, I didn't even see my own negative. I saw it up there, not here. Okay, so second d first, negative 2. Plus first, negative 2x. D second, what's the derivative of y? And that, whoo! Second, bottom, d top. That was just the derivative of the top. Minus, whoo!
Top.
Top, okay, keep them the same. 4 minus 2xy. D bottom, oh, whew, that's easier. 2x. All over, bottom, squared. X squared is x to the 4. That's what is on that sideboard. Now, what's the dilemma, though, when we go to simplify?
We have things being multiplied and distributed.
Yeah, we have yuckiness all over, and we have a dy dx. Now, I personally deal with the dy dx last. So I say, this little x squared needs to come in to both terms, right? All right, so I'm going to draw my fraction. Woo! Put my x to the 4th. I have a negative 2x squared y. I'm just writing the x squared first because you usually do alphabetical order. Plus, well, it's going to be a negative, so minus 2x cubed. Why am I showing parentheses and leaving it blank?
Because you go plug in.
I'm going to plug in a second. Minus,
8x.
I have 8x, and then
Plus
I'm going to put
4x
this
for
one.
y.
Yeah. Okay, so it's going to be minus 4x squared y, but you guys are distributing the negative, I think, right?
Yeah.
Okay, so the negative is going to go to the 8 and to the negative 4, which means you're going to have a minus 8x and a plus 4x squared y. Okay, who's my dy dx?
4 minus 2xy over x squared. Which is nice.
Not so shabby,
Which is nice.
because my trick just says you don't need to get common denominators and make him an over 1 and multiply by reciprocal. All I have to do is multiply top and bottom by.
X squared.
That's all you got to do.
Yeah, because if we multiplied in, it would just cancel out.
So not only would it have been easy to simplify the complex fraction, but a few of your classmates are like, wait, we don't even need to do a complex fraction because what is that expression getting multiplied by? X cubed. So the x squared and the x cubed reduce. And you end up with negative 2 x squared y. Uh-oh, is it time to distribute?
Yes.
Okay, so we have negative 8x and a positive
4x squared y. Yes.
minus 8x. What?
Yes. And some of you guys are seeing there are quite a few like terms, true? Because all of the xy terms are matching, x squared 1. We have a 4 plus 4 is 8, and 8 minus 2 is 6. And negative 8x and negative 8x is, All over x.
and maybe you guys also see
Hold
that
out
you
the
share
x.
x. Oh, sorry, I already simplified. Let's get it. If we really wanted to, I suppose we could pull out a 2. That's kind of lame, though. I think you guys can make it match if the 2 is not pulled out. Pause. If it was long answer, you would have had to have waited to box until this step.
Yeah.
Because you have to get dy dx in. As soon as you have it in terms of x and y, you could have boxed it. But this won't be a long answer. On a test, it might be. Yeah, technically you could box it right there. Yes. Charlotte.
I don't know what
Well, we've been walking through step by step, right? So where did yours go differently than mine? Okay, so this is the same. I got that too. You pull an X out of everybody? You simplified the early thing. Then you plug in.
Wait, where was
Alright. I'm checking it.
Notice, like, everybody's all this.
I didn't even notice. This is
Kiddos, pause. I'm dual paging really fast so that you guys can keep taking the next page. Because technically in homework, logarithmic differentiation comes in. And I think we're going to maybe save one until tomorrow. But we need to do at least one or two. Technically, I think today is going to be a finished section 2.5 grade, which you were able to get done in homework. And probably not go to section 2.6, which is okay. Then tomorrow we'll finish grading 2.6, like maybe 70s and beyond, because maybe you got stuck around there. Maybe even like the 60s you got stuck. So let's go ahead and just focus on finishing 2.5. So there's a new page up there. You guys should be taking notes. I'm just checking Charlotte's work real quick. She pulled out an X early,
And some of her terms were swapped, like written backwards, but they're still good. Something just went. Oh, silly mistake.
Just look out one term, and you messed up my whole problem. -2 1.
I think it's your signs you're on. Yeah, that's it. Cool. That was tricky. All right. I'm going to go ahead and zoom in on the second page. We actually talked about this a little bit early. It was before we had learned implicit differentiation. I just was showing you it was a thing back when we had logs. Except, question.
So what would you raise both to the third power? This was in the wrong.
Well, if you read the directions at the top, it says logarithmic differentiation. Doesn't that mean you're supposed to have a log before you can use log properties?
That's you.
So let's put ln. Yeah, let's put ln in. So this is the one that we didn't get to finish solving earlier because I was like, ooh, we haven't learned this thing called implicit differentiation. We had a test coming, so we just kind of breezed by it.
Can I just cue this?
You could cube both sides, that's true. But since it's in the logarithmic differentiation, I'm just showing you how you could use ln. But you could cube both sides and use implicit that way as well. It does work. But if we were to use ln, just showing the logarithmic differentiation, couldn't we rewrite this as this guy? To the 1/3 power. And instead of having to think about u to the 1/3 being 1/3 u to the -2/3 times u third, we could just do what?
Bring the one down.
Yeah. We could just bring the 1/3 down and have ln of u. Okay, ln of the other side. Then what are we going to do now that we know implicit? Are we scared of ln of y? Hopefully not too much. Or even up here, when Charlotte and Tyler both said, hey, can't we just cube both sides, would we have been scared of y cubed? Hopefully not. Because you can just take the derivative of both sides, right? Which is technically what we've been doing all along. How do we take the derivative of ln of y? 1 over y, which is like 1 over u. But times dy dx equals. And over here, we would just 1/3, right? Because he's a constant multiple. Times. Okay, how to take the derivative of ln of blah. Chain rule. So 1 over u, which is that whole thing, 2 plus tangent of x squared. Ooh, but what do we need now? So if you need to, when the u's get hard, sometimes it's good to write them off to the side. 2 plus tangent of x squared. The derivative of 2 is 0. Okay. How would I take the derivative of tangent of, ooh, isn't that like a v or like a u? How would I take the derivative of tangent of block, tangent of v, tangent of x squared?
Secant squared of block.
Secant squared of, keep it the same, but I also need my my 2x.
Actually, that would make a lot of sense.
It takes time.
I mean, like, I've been doing U's and U's make sense too, but I mean, blobs.
It takes time. As you get more used to it, then the blobs or even just the thinking about it just becomes more automatic, but you have to have a lot of practice before it becomes automatic. I put the 2x in front. So its derivative of the outside was secant squared, keep the inside the same, times the derivative of x squared was 2x. That's our u prime. That's our chain rule. Then just move them in front. So that's what I need to add in right here. We could simplify the right-hand side just a little bit. We end up with keep the 3 out, I suppose. The question is, how would I get dy dx by itself?
Multiply by 1.
Good. Multiply one side by one, which you do one side, you have to do to the other side. But do you think I'm going to keep it y? I could. But in the very beginning, did they keep it y?
No.
I should say this one. In the beginning, was it implicit? Was it in terms of x's and y? So you have to plug in the original expression for y, which in this one is pretty nasty. And to be honest, I would say it would have been easier to probably not use logarithm differentiation. Because at this point, this would not be a multiple choice answer. It's a cube root. Because you have a 2 plus tangent x squared to a 1/3 power up top, and you have a 2 plus tangent x squared to the 1 down bottom. Do you guys remember what we do to exponents when we have like terms or bases on the top and the bottom? Like x squared over x to the 5th. What would we do with those exponents? We would cancel by subtracting them. So this one's 1/3. This one's 1. What happens when we subtract 1/3 minus 1? Yeah. Which some of you are like, man, I could have done negative means in the denominator. Some of you are like, well, I should have just made that 1/3 and done power rule. It would have been easier. That's true. I was just showing you there was another way of going about doing this one. Now, the only reason, in my advice, the only reason you would add in a logarithm if there isn't one is if they ask you to solve using logarithm differentiation. Otherwise, to be honest, I think the logarithm actually made this problem a little bit longer. It would have probably been easier to raise this guy to the 1/3 power and just do chain rule carefully, or to cube both sides and use implicit. But if they say logarithm differentiation, the answer is going to look like they took one of both sides. Yeah.
One thing, so on your second to second last step, yeah. Why does it become 2x squared secant? Like, why is it x squared?
Oh, because I randomly put in the square thing.
Oh, okay, I wasn't wondering.
No, thank you for catching me. And there's a lot of stuff going on, and I'm trying to write and explain while putting answers. Sometimes stuff gets funny. I have a friend that always says her smartboard makes her dumb. She tells her kids that. Smartboard makes me dumb. I get focused on other things and then be distracted and make mistakes. But I think for me it's talking. Hey, the Bible says, even a fool can appear wise when he's silent. bad I can't be silent in the classroom and teach at the same time. So the foolishness comes out.
Record yourself and play a video.
Great. Then I'll be recorded even better.
Oh my god.
Kiddos.
Right, let's not freak out. Let's not freak out.
Okay.
Freaking out.
It says using logarithmic differentiation, which means you're supposed to take an ln. Now, pause. I mean, it would be fun and all to do a quotient rule, right? Because, look, you'd have bottom, be top. Ah, it's a product rule and a chain rule and a... Okay. Let's see if LNs make this one maybe even better than the last one. The last one's like, did it really make it easier? I'm not so sure. But how about this one? What are we going to do to both sides?
Do an LN.
Yeah, we can't do logarithmic differentiation without a log. And are we going to put like a log base 7? No. Who's the easiest log formula? LN. That's why I told you last year to use LN. How can we rewrite? This one stays. How are we going to rewrite that one?
You can break it up top and bottom.
I can break up the top and bottom with a minus, but can't I also break up the top with a plus? Pause. Isn't this a multiplication, and isn't there a property for ln of a times b? Isn't it ln of a plus ln of b? Give YouTube free count properties beginning of our log section. Ln of a times b is ln of a plus, so I can put ln of x plus ln of x minus 1 to the 3 halves minus, and look at these little baby guys, so much nicer, minus ln of, isn't square root the same thing as the half power? Now they show the little inequality just to basically say this is legal. Sorry, typo. That should be x greater than negative 1. No, it's x greater than 1. Negative 1 would have been the square root, but ln's, remember, they have to be a positive number, so it actually does have to be greater than 1. This is just saying, don't worry, we're only taking the derivatives for those values that are in the domain. That's all that's saying. Is there any other super cool property of ln's that we can use to simplify even more? Yeah. No derivatives, we're just using free count.
One question.
Yeah.
Why would the 1/2 not be negative because it's at the bottom?
No, it is.
We did the subtraction to signify the division.
Okay.
If we do another negative, then we're going to double do it, and we're going to end up undoing it. Which is that. What can we do to both sides, cool kids?
You can. Oh.
Go for it. I know, but look, it's addition and subtraction. Isn't that easier than this big old mess? Hopefully. Hopefully easier. If you remember your rules. 1 over y. Don't forget it's a y. So times y prime. What's derivative ln of x? The 3 halves can just be a fraction, right? We'll keep them. The derivative of ln of x minus 1 is not 1 over x minus 1 times u prime. But what is the derivative of x minus 1? It's just an x. So derivative of x is 1, derivative of 1 is 0, it's just times 1. That's nice. If it was 2x minus 1, the derivative would be 2. Just the derivative, yeah, we're just driving here. And then we have a 1/2. Derivative of ln of u is good, 1 over u. And what's the derivative of x plus 1? Derivative of 1 is 0. Derivative of x.
Oh, the derivative of x.
Yeah, there you go. So we end up with 1 over x plus 3 over 2 times x minus 1 minus 1 over 2 times x plus 1. And we're almost to the derivative. How do we get dy dx alone? Multiply by y. What we do on one side, we do on the other. To finish off and get dy dx, we say, I'm just doing this because this is what they almost always do. At the very beginning, it was only in terms of x. At the end, they only want it in terms of x. So we're just going to take who was y.
But, oh, you gotta be kidding me.
No. Don't stress. If they have asked you to do this, on the AP specifically, they will never simplify further. If they ask you to do logarithm differentiation, they expect you to end. Just kind of things.
Very nice.
Now, if it's in the book and you're making it match, what could they have done? I'm just showing what could they have done. They could have gotten common denominators. So multiplying this guy by x plus 1, multiplying these two by x minus 1, and these two by x and x, and put it all together, and then moved all that in.
So what you're saying is the book people don't have a soul.
No, the book people probably would have solved it. Unless they said using logarithm differentiation, they would have solved it with the quotient rule and product. And that would have gotten one huge old fraction simplified after that. But if it says logarithm differentiation, this is technically where I'm totally fine with you stopping. Sound good?
You know what? Fine.
Let it rain. Okay, so
Oh,
last one. I wanted to check the evens.
So hard. We don't have enough time. Class is maybe an hour.
That's why I said, just give us one more, like, 3 more minutes. One more 3 more minutes.
Does this mean I know?
Probably come on.
oh.
Oh, yeah, I said it. Okay. This is our last example, guys. I'm going to go quick.
Wow. Can you just give us a
I'm
copy?
going to go quick. You ready? They said logarithm differentiation.
Alright, what time
makes
did you
absolute
go?
sense. Somebody can go ahead and.
1 second.
We're at 5 seconds now.
Oh, I have
We have more than
We're at
5
10
seconds,
seconds.
David. David, get out of the class.
We're at 15 seconds.
Right there. Oh.
You're at 20 seconds.
I haven't done it yet today. It's not
You're at
memorized
25
yet.
seconds. You have arrived at 30 seconds.
Actually, a samurai.
Don't worry, Sean. It's
Okay, and then you multiply by 1. I know what she's doing. I'm not worried about that. It's just add the y. This is really fast.
we started.
Okay, you can check it out online.
You did
If you
that
want
53
to.
seconds.
Woo!
Oh my gosh.
You're welcome.
That would have taken.
Man, that was pressure. I totally thought it was that long until the bell. I still have it. Okay, pause. That's the last example. You can look at it online if you want. Here's what's going on. I am going to scroll right now, very quickly, quicker than you could possibly check through the evens. What can you do tonight?
Chuck them.
I'm recording.
Let me see any shit.
Go on YouTube. Pause. Check your evens. Come tomorrow with questions on odds and evens that you cannot make match.
What did you get for that one?
Give me 1 second. Let me finish scrolling. So wait, what are you supposed to do besides finish attempting homework? Check the evens. Come tomorrow with any questions on ones that you could not make match. Bye, cool kids.
Sweater designs.
Sweater designs tomorrow. Bonus. Have it printed and or written, drawn, and or emailed. Bye.
Poorly drawn. 5 of them.
We'll start loading next week.